All right, so this is called electromagnetism in a nutshell. This is going to be quite difficult to try to do normally in school. We have a couple of weeks to do all this, and there's demonstrations, and there's a lot of hand motions actually required to teach electromagnetism in high school. And that's going to be pretty hard to do with webcam here. So I'll do my best, but you'll get a more full treatment hopefully in grade 12 if you're taking grade 12 physics. Okay, so there's 5 concepts I want to talk to you about that relates to both electricity and magnetism, okay, and how they're related to each other. That's why it's called electromagnetism, because you might not know that they're related to each other. You may know some things about electric charges on their own, which I've summarized on the left of this slide. This is from grade 9 actually, that there's 2 types of charges, positive and negative, and that like charges repel and unlike charges attract. Okay, so I just got some pictures here. So a positive charge and a positive charge, if you hold them beside each other and let go, they're going to repel. Same with a negative and negative. However, if you have opposite charges, so one positive, one negative, and you hold them there and then you let go, they're going to attract together. Okay, so that's how electric charges behave with attraction and repulsion. And then you may know a bit about magnets, maybe just by playing around with magnets as a kid. Maybe you might learn about them in some elementary school grades as well. There's 2 poles, okay, we call them poles, the North Pole and the South Pole of a magnet. And very much like electric charges, the like poles repel and the unlike poles attract. So if you have 2 bar magnets and you hold the same poles close to each other, you're going to feel a force of repulsion. However, like the very last diagram, if you hold 2 bar magnets with opposite poles near each other, then you're going to feel them go close together and they're going to stick together if you let them. Okay, so it seems like electric charges and magnetic poles behave the same way, but they're 2 different things. Okay, so you may ask, well, what if you take one of the one and another of the other? So if you take one electric charge, I just took a positive charge as an example, and you put it next to a magnetic pole. So if we put a positive electric charge next to a south magnetic pole, we hold them at rest, and then we let go, what are they going to do? Are they going to attract, or are they going to repel, or neither? So the answer to the question I just said out loud is nothing, okay? So if both objects are at rest, then they will not apply any force on each other. However, what's pretty tricky and complicated is that if they're not at rest, then the answer may be different. Okay, so it says, however, charges and or magnets in motion can have an effect on each other. Okay, so if I leave them at rest here, they're not going to do anything to each other. But if one or the other of them is moving, then they might start to have an effect on each other. And so it's, yeah, it was discovered not too long ago, just like a couple hundred years or less ago. But as we learn more about it, we've been able to create like advanced society a lot more through electricity and magnetism. It lets us create electricity on a large scale that can be distributed to an entire country, well, the whole world, really. Okay, so I want to try to go over the main concepts behind electromagnetism. So there's 5 of them. Concept number 1, an electric current produces a magnetic field. So this is a concept also called Ørsted's law, named after the person who kind of accidentally discovered this. He was teaching physics, and this was 1820. So that's why I said about 200 years ago. He was teaching physics, and he just had he was doing some electricity lessons. Okay, but he also had some compasses sitting around too. So compasses are magnets, like they respond to magnets. And what he noticed was that every time he turned on a current, like a large current for a demonstration for electricity, he noticed that the compass needle moved. And when he turned the current off, the compass needle moved back. Okay, so by turning the current on and off, you notice it caused the compass needle to spin a bit. All right, and that's kind of the first discovery that maybe electric charges can cause a force on magnets and vice versa. Okay, so if you have a straight wire, this is a straight wire, and you put a current through it, and the current's marked in red there, it's going to actually create a magnetic field around it. The magnetic field is going to go in circles down the length of this wire. So if you were to put a compass anywhere inside of these circles, the compass would change and point in a different direction. It would point in whatever direction these circles are going. Okay, so that's concept number one, that moving charges or an electric current is capable of acting on a magnet. So then they took that idea and they engineered something out of that. Okay, so instead of having one long wire that creates a magnetic field around it, that's actually quite a weak magnetic field. However, if you take that wire and then you wrap it around and around and around and around and around and around into a coil, like this picture shows here, a coil, then what you do is you take these tiny magnetic fields. So each of these circles is like a tiny bit of a magnetic field. And as you wrap this into a coil, a lot of the magnetic field gets concentrated up through the middle of the coil. So in that way, you can kind of make a much stronger magnetic effect. So that device is called a solenoid. That's just the name we use for a coil with current going through it. It's called a solenoid. And further, they discovered that certain metals, such as iron, can be magnetized. Okay, so if you ever took a magnet, you realized you can pick up some paper clips using a magnet. Okay, so the material of paper clips, which is iron or steel, it can be magnetized. So if you stick a large chunk of iron, which is shown right here, into the middle of that coil, then that piece of iron gets magnetized. And that's going to actually make this quite a powerful magnet together. Okay, so the coil with the iron core in it can make quite a strong magnet. And the picture on the right here shows something like that. That's picking up metal from a scrapyard. Okay, so we call this an electromagnet because it's a magnet that can be turned off or on with electricity. Okay, so this only becomes magnetized when there's a current running through the wires. So when there's electricity running through it. But what happens if you turn off the electricity? Then it loses its magnetism. So that actually makes this large electromagnet pretty useful, because then you can turn on the electricity, which creates a magnet, and pick up all this stuff. Then you can move it somewhere else, and then you can turn off the electricity, and then that'll make it lose its magnetism. So all that material you just picked up will just get dropped wherever you want to drop it. Okay, so that's an electromagnet, an application of Ørsted's discovery. All right, how about the other way around? Okay, so we've established that a current, so moving charges, are able to create a magnetic effect. Well, what about the other way around? Can a magnet apply a force on a moving charge? And the answer is yes. Okay, if you have a charged particle, like a proton or an electron is a charged particle, and you fire a beam of those protons, you fire a beam of those charged particles into a magnetic field, that magnetic field is going to cause that beam of particles to curve and change direction and deflect. Okay, so a magnetic field is capable, or it does, apply a force on a moving charge, and it causes those charges to deflect in an arced path. One nature example of that would be actually the aurora borealis effect. So if you go far enough north, so it's usually you can't see it in the GTA, but if you go to like the Yukon Territories, Northwest Territories, Alaska, you may be able to see the aurora borealis, which is like a greenish glow in the sky. And what that is these charged particles getting neutralized, I think. I have to double check that, but these charged particles kind of neutralizing in the atmosphere. And why does it happen when you go further up north? Why can't we see it around here? Well, that's because the Earth, for whatever reason, has its own magnetic field that it creates around it. Okay, so these blue lines labeled with B, B is the symbol we use for magnetic field. The Earth naturally creates its own magnetic field. That's why when you have a compass, you're hiking or something, you have a compass, the compass points north. It's responding to the Earth's natural magnetic field. So there can be charged particles coming from outer space, and as they enter the Earth's magnetic field, they get deflected. Okay, they get deflected by the magnetic field, and just the physics of it, it causes it to curve. Okay, so those particles curve and they spiral and get directed towards the north and south poles. So that's why you see it, the aurora borealis. You have a better chance to see it the more north you go. Okay, so but the point is that magnets can apply a force on moving charges. Magnets can apply a force on moving charges. And that concept was used very cleverly to design electric motors. Okay, and electric motors are extremely useful things. The simplest example I can think of would be just an electric fan. It's getting close to summer. It's getting hotter these days, so I've been plugging in fans. And electric fans, all they do is they take electricity, they take electrical energy, and they turn it into mechanical energy or spinning energy, rotational energy. So this diagram here is showing kind of like a conceptual diagram of how a motor would work. So you have a battery, which causes a current to go through this wire here. I'll follow the arrows. The current's going this way through the wires. Okay, but a current is moving charges. And moving charges can feel a force from magnets. So here's a big magnet here. So this magnet is applying force to the charges moving through the wire. And if it's designed just right, so this red and blue thing here, that's part of the design. It's actually kind of a tricky design, but if it's designed just right, you can cause the loop of wire to spin. Okay, so that's taking electrical energy from the battery and turning it into rotational mechanical energy, something spinning, kinetic energy. All right, and that's an electric motor. It used to be that automobiles were run by gasoline, right? So it's not an electric motor. It's a fossil fuel powered motor, but now we're getting to design electric motors for cars as well. So that's up and coming. There's the Teslas, I think, are electric vehicles operating right now. Okay, so there's a couple more concepts to get through that I'm going to have to do in another video because I'm out of time for this one.